In today's video, we look at our first of two methods of evaluating a determinant, known as reduction to triangular form. So this video will broadly be in two parts. I should say two sections. The first section is the actual development of the method itself, as well as an example of using the method. Then the second section will be some more properties of determinants, which can now be proven using this new method that we have derived. So the first step of our method is to prove the following property. If a matrix B results from matrix A by interchanging two different rows of A, then the determinant of A is equal to negative determinant of A. I'm sorry, this should be the determinant of B is equal to negative determinant of A. So, let's first suppose that B arises from A by interchanging rows R and S. Now, without loss of generality, suppose that R is less than S. So row R comes before row S. Now, what without loss of generality means is that even if R was greater than S, the proof is the same. If the logic follows identically. So we can just assume that R is less than S and not lose anything. Then, notice that we have BRJ is equal to ASJ and BSJ is equal to ARJ. This is what it means to interchange two rows. Let's also just add that BIJ equals AIJ for all other i's. That is, for all the i's that are not equal to R nor S. Now we can go ahead and look at the determinant of B. Remember, by definition, this is going to be plus or minus B1J1, B2J2, so on and so forth, BNJN. Let me do this, actually, BRJR, BSJS, and then BNJN. Replacing all of our B terms with the associated A terms, we have A1J1, A2J2, AR, AS, JR, then AR, JS, and finally AN, JN. Now let's just move our ARJS term to come before the ASJR term, just so that we have the row indexes in ascending order. Take a look at this permutation. J1, J2, JS, JR, JN. This results from the permutation J1, J2, JR, so on and so forth, JS, so on and so forth, JN, simply by an interchange of two numbers. Furthermore, the number of inversions in the former will differ by an odd number from the number of inversions in the latter. Therefore, the sign of each term in the determinant of B is the negative of the sign of the corresponding term in determinant of A. Since all of the terms are negatives, so all of the terms in determinant B are negatives of the corresponding in determinant A, we thus have that the determinant of B is equal to negative determinant of A as desired. As a direct corollary of this, if two rows of A are equal, then the determinant of A is 0. So we shall suppose that rows R and S are equal. Interchange these two rows. This gives us a matrix B. Then, by Theorem 1, which we just proved, the determinant of B has to equal negative determinant of A. On the other hand, the matrix B is equal to the matrix A, right? Because rows R and S are the same. So interchanging those two rows will not change the actual matrix. So since it's the same matrix, we should have the determinant of B is equal to the determinant of A. This means that the determinant of A is equal to the negative determinant of A. And the only way this is possible is if the determinant of A is equal to 0. The next property for our method: if B is obtained from A by multiplying a row of A by a real number K, then the determinant of B is equal to K times the determinant of A. So suppose that the rth row of A Aij is, learn how to spell, is multiplied by K. to obtain the matrix B, Bij. Then what we're going to have is Bij will equal Aij whenever I is not equal to R, and K times Arj when I is equal to R. Now we can take a look at the determinant of B. And again, by definition, it's the summation plus or minus B1J1, B2J2, right, so on and so forth, then BRJR, right, and then so on and so forth, BNJN. Right, then this is the summation plus or minus. Replace all the B's. Right, now remember BRJR is going to equal K times ARJR. And then ANJN. And let's just put this in parentheses for safe measure. Now that K is a constant, so it can be factored out of the summation. And this is what we're left with. But this is precisely this summation, the determinant of A. So we have determinant of B is equal to K times the determinant of A. The third property we need for our new method, if B is obtained from A by adding to each element of the rth row of A, K times the corresponding element of the s row, where R is not equal to S, of A, then the determinant of B is equal to the determinant of A. In other words, if the matrix B is obtained from a matrix A by multiplying a row by a constant and adding to another row, then the determinant does not change. Now, notice what we have here. Bij is going to equal Aij whenever I is not equal to R. And then Arj plus Kasj whenever I is equal to R, with R not equal to S. Now, without loss of generality, we can assume that R is less than S. Then, let's take a look at the determinant of B. Right, by definition, replace the B's with A's. Right, then by distribution and properties of summation, we can write this as two separate sums. First is this. And then the second is this. Now, this first term is the determinant of A. Right? So take a look now at the second term. We can factor out a K, and then we're left with this. Now this is equal to 0 because this is the determinant of a matrix with 2 equal rows. Right, so then that means that this entire term here goes to 0, and what we are left with is the determinant of B is equal to the determinant of A as desired. Final property we need for our new method: if a matrix A is upper or lower triangular, then the determinant of A is A11 times A22 times so on and so forth times ANN. In other words, the determinant of an upper or lower triangular matrix is the product of the main diagonal entries. What we will do is first let A be upper triangular. Right, then the terms A1J1, A2J2, so on and so forth, ANJN can be non-zero only for 1 less than or equal to J1, 2 less than or equal to J2, so on and so forth, n less than or equal to J sub n. Right? These are the terms in the upper part of the matrix. Right, but J1, J2, so on and so forth, Jn must be a permutation of the set S equals the integers 1, 2, up through n. So what we find is we must have J1 equal to 1, J2 equal to 2, so on and so forth, Jn equal to n to have a non-zero term. Right? This implies the only term of the determinant of A that is non-zero is A1J1, I'm sorry, A11, A22, so on and so forth, ANN. This means the determinant of A would be this term plus a bunch of 0 terms. Well, when you add 0 to anything, it's still the same number. So it's just A11, A22 through ANN. This is what we desired. Now the proof for lower triangular is very similar and is left as an exercise. So that completes this proof. We can now combine these 4 properties for our method. And this is known as the method via reduction to triangular form, or simply the method of triangulation. So this method reduces the square matrix into an upper or lower triangular matrix using elementary row operations, keeping track of each operation and the constant that will have to be multiplied to the resultant determinant. Right then, all we do is we multiply the elements of the main diagonal of the triangular matrix and the constants from the operations performed to find our desired determinant. Okay, so there's really only two that you have to keep track of. Interchanging row I with j results in multiplying by -1. Multiplying a row by a constant k results in multiplying by a 1 over k. We will now go ahead and use this method to find the determinant of this, 5 by 5. So here's what we do. Start with the actual matrix. Now, the goal here is not to reduce it into REF. It's just to reduce it to an upper or lower triangular. By default, I will be converting it to an upper triangular at all times. Since that is our goal, we take a look and we say, well, it would be easier to deal with this one up in the first row. So let's go ahead and switch row 1 with row 5. Now remember, we're switching rows, so the result will be multiplied by -1. Now we just want to zero out everything below this top one. And since this is just adding multiples of row 1 to each row below it, it does not change the determinant. So we don't have to worry about multiplying by any constants. So it'll be 2 row 1 plus row 2, negative row 1 plus row 3, negative 3 row 1 plus row 4, negative 2 row 1 plus row 5. All right, we're still going to have that negative out there. Now again, it's going to be easier to deal with that -1 than that 3. So let's just go ahead and swap row 2 and row 3. Right now, this of course means we're multiplying again by -1, so that negative is going to disappear. Zero out everything below that -1. Right, so 3 row 2 plus row 3, -4 row 2 plus row 4, -2 row 2 plus row 5. And again, there's no need to multiply by a constant. Now, if we look below that -3, everything below it is a multiple of 3. So, no need to switch any rows, do anything fancy. It'll be 3 row 3 plus row 4, and then simply row 3 plus row 5. Now we look and decide it might be easier to work with this 5 rather than that 16. So let's go ahead and switch row 4 and row 5. That means we're going to have to multiply by a -1. Okay. Now, let's go ahead and do one final step. Multiply 16/5 row 4 and add it to row 5. That will leave us with this matrix. I forgot my negative. And now what we want to do is just look at the lower terms. They are all 0. So we now have an upper triangular matrix. So this will equal -1 times 1 times -1 times -3 times 5 times 9. And that whole thing is equal to -135. So the determinant of our matrix is -135. We now move into the second section, which is, again, just looking at some more properties of determinants. So first we need a lemma. So a lemma is typically a property that is needed to prove another property. All right, so lemma 1, if E is an elementary matrix, then the determinant of E times A is equal to the determinant of E times determinant of A, and the determinant of AE is equal to the determinant of A times the determinant of E. Now remember, we have three types of elementary matrices. We have to look at each one. First, if E is an elementary matrix of type 1, then EA is obtained from A by interchanging two rows of A. So this means that the determinant of EA is equal to negative determinant of A. Also, E, remember, is a triangular matrix. It's both upper and lower. So interchanging two rows, we'll multiply by negative, and since it has ones along the main diagonal, its determinant, is negative 1. And so what we see is we have determinant of EA is equal to determinant of E times the determinant of A. And of course, this is also equal to determinant of A times determinant of E, right? So the order doesn't matter, so we're done. If E is an elementary matrix of type 2, then E times A is obtained from A by multiplying a given row of A by a constant K not equal to 0. Then the determinant of EA would equal K times the determinant of A. Also, however, notice that the determinant of E would be K. So we have, once again, the determinant of EA is equal to the determinant of E times the determinant of A. Now, if E is an elementary matrix of type 3 now, then EA is obtained from A by adding a multiple of a row of A to a different row of A. Then what we have is determinant of EA is simply equal to the determinant of A. Also notice, though, that the determinant of E would remain unchanged, so it's equal to 1. Therefore, the determinant of EA is once again determinant of E times determinant of A. And so the proof is complete. For the property we need this for, if A is a m by n matrix, then A is non-singular if and only if determinant of A is not equal to 0. And that should, of course, not be m by n, right? That should be n by n because determinants only exist for square matrices. So, if A is non-singular, then A is the product of elementary matrices. So, let A equal E1, E2, so on and so forth, up through EK. Then, by lemma 1, we can write this. Determinant of A is, of course, the determinant of this product, which is now the product of this. Which is guaranteed to be non-zero, right? Because the determinant of an elementary matrix is not 0. If A is singular, then A is row equivalent to a matrix that has a row of zeros. Again, because we're dealing with a square matrix. Then A is equal to E1, E2 up through EK times a matrix B, where each EI is an elementary matrix. Right, so what we can write is that the determinant of A is equal to this determinant. And again, by lemma 1, we can write this product. However, by corollary 1, that is 0, because the determinant of B is going to be 0. It has a row of zeros. And so, we've proven both directions. And so we've completed this proof. Now, as a corollary, if A is an n by n matrix, then the system AX equals 0 has non-trivial solution if and only if the determinant of A is equal to 0. Let's start by assuming that the determinant of A is not 0. Then A is non-singular by Theorem 5. And thus, the system AX equals 0 has only the trivial solution. Conversely, if the determinant of A is 0, then A is singular. Suppose that A is row equivalent to B, which is in RREF, right? Then B cannot be the identity matrix, which means that B has a row of zeros. Also, notice that the system's AX equals 0 and BX equals 0 have the same solution set. Now, let C be the matrix obtained by deleting the 0 rows of B. Then BX equals 0 and CX equals 0 have the same solution set. Now, since the latter is a homogeneous system of at most n minus 1 equations in n unknowns, it is guaranteed to have a non-trivial solution. Therefore, AX equals 0 has non-trivial solution. Now, if A and B are n by n matrices, the determinant of A times B is equal to the determinant of A times the determinant of B. We have two possibilities here. We have that A is non-singular and A is singular. So let's start with A is non-singular. Then we know that A is row equivalent to the identity matrix. Right? So A would be EK times EK minus 1 times E2 times E1 times IN, which of course is just EK, EK minus 1, E2, E1, where each E sub I is an elementary matrix. So, determinant of A is the determinant of that product. Which of course we can write as this product. This allows us to write the determinant of A times B as the determinant of that product of elementary matrices times B, which allows us to write it as this product right? But of course, as we've just shown, this is the determinant of A. And so we're done if A is non-singular. If A is singular, though, then the determinant of A has to be 0. Right? That is by Theorem 5. Moreover, A is row equivalent to a matrix C that has a row of zeros. Therefore, we can write C as EK times EK minus 1 times E2 times E1 times A, which means that C times B is this. Which of course means that CB is row equivalent to, I should have said AB here is row equivalent to CB. Now, since CB has a row of zeros, it follows that AB is also singular. And this, of course, means that the determinant of AB must be 0. And since the determinant of A is also 0, we can say this is the determinant of A times the determinant of B as desired. And so our proof is complete. As a final property, a corollary of this, if A is non-singular, then the determinant of A inverse is 1 over the determinant of A. And of course, the proof of this is fairly straightforward. It should follow almost directly from the theorem we just proved. And so would be left as an exercise. So that concludes our video on the method of reduction to triangular form. In the next video, we are going to look at a second method of evaluating determinants, known as the method of cofactor expansion. That video will be a lot shorter than this one. There's not much properties to prove. So as always, thank you for watching this video. I hope you enjoyed, and I will see you all in the next video.